Hello students, in this video we'll discuss the relationship between the algebraic value of a covariant derivative and the angle between two unit vector fields. So let's be given a surface S and two unit vector fields W hat of t and V hat of t on remember that for these vector fields, they have to take values on the tangent space, right? So taking values on the tangent space of S at every point t. Okay, beautiful. And so now let's recall. So what this is recall that the covariant derivative of these things is the covariant derivative. And the covariant derivative is the projection of the derivative onto the tangent space. In other words, this is the orthogonal projection of V hat onto the tangent space. Okay? In other words, what you can say is therefore dv dt is really what? dv dt is really v prime minus v prime and then n hat. So you subtract off the normal components of the derivative. Okay, so that's what the orthogonal projection is. Beautiful. Okay, and so now let's do this. And so I'm going to define. And so recall also that in this situation we also know that's dv dt in the case of a unit vector is really some number lambda times what? Some number lambda times n hat cross v, like this, because it has to be perpendicular. Since it's a unit vector, it's perpendicular to v. The derivative is perpendicular to v hat, and it's also perpendicular to n because I'm subtracting off the normal components. And we also see that this value lambda, so this value lambda is the algebraic value. Is the algebraic value, and we write like this. So lambda is really the bracket dv dt. And in this case, we can see that this value lambda is also equal to what? It's the inner product of v hat with n hat cross v hat, like this, right? So that's the value of what lambda is. So this gives us a formula for lambda. Beautiful. Okay. And so now what will I do? So now here's the proposition. We want to discuss the angle between two unit vector fields. So let's let phi be the angle between V and W. Okay. Then I want to relate the relationship that I want to compute how this value phi and how phi changes, how that relates to these algebraic values of the covariant derivative of each of these terms over here, right? So hence, let's do it like this. So we know that W hat, for example, has to be what? W hat has to be the cosine of phi, V hat, plus the sine of phi, and then some orthogonal components. I'm going to call it V hat bar. Well, what's V hat bar here? V hat bar is going to be n cross V hat. And then similarly, W hat bar is going to be n hat cross W hat, right? And so what will W bar be? So then W bar hat is going to be negative sine of phi V hat plus cosine of phi V hat bar, like that. Beautiful. Okay. Now let me compute the derivative of this expression over here. Okay. So what is W hat prime? Well, it's going to be cosine phi V hat prime plus sine of phi V hat bar prime plus what? Plus cosine phi prime, and then v hat bar minus sine phi v hat, and then phi prime, like so. Okay. Now let me compute the inner product of w prime with w. And what's the inner product of w prime with w? The inner product of w prime with w is exactly going to be the algebraic value of the covariant derivative of w. So in other words, the algebraic value of the covariant derivative of w is going to be the inner product of w prime with w with n hat cross w. But n hat cross w is exactly equal to what? That's exactly equal to w bar, right? So this is going to be w prime, and then with w hat bar, like that. Great. Okay, because we're using this formula right down over here, right? Okay. So now let's do these things slowly. So here's my formula for w hat bar, right? Here's my formula for w prime. So let's do these things one by one. So let's look at these terms over here. So this term over here dot this term over here is going to be v dot v prime. Well, what is v dot v prime? So recall, so note that since these are vectors, v hat dot v hat prime is equal to 0, since they're unit vectors, right? The same thing for the bars, right? So this term over here dot this term is going to give me a 0 because they're perpendicular. This term over here dot this term over here is going to be a cosine squared phi, and then I'll have a v hat prime and then a v hat bar. That takes care of these terms over here. Then this term over here dot this term is going to be a minus sine squared phi, and then v hat prime. Okay. Then this and this over here are going to be 0 because there's a unit vector. So this term with this term is gone. Then we're going to have a phi prime cosine square, then a negative cosine sine, and then v bar. Okay. So that's going to be a negative sine phi cosine phi, negative sine phi cosine phi prime. And then over here we'll have a v with v hat bar. But let's think about that for a second. So what's the relationship between, what's the inner product of v hat and then v hat bar? Well, v hat bar and v are perpendicular, so this term is actually 0, right? So that term is actually gone because they're perpendicular to each other. So in other words, when I do the inner product of this and this, I get nothing. Then I'll have a cosine squared phi prime, and then that's going to give me a 1, so that's going to be a cosine squared phi, and then a phi prime, like that. Beautiful. Then I'll have a plus sine squared phi, and then phi prime, like that. Beautiful. And then finally, if I do this and this, I get nothing over here, right? Good. Now, what are we going to have over here? So now the key feature is that I can pass derivatives over here from one thing to the other, right? And so these two terms over here are nothing more than just the inner product of v with what? So if I put the derivative on the v prime over here, then what we'll have is we're going to have, so again, I'm going to write this as cosine squared phi, and then v hat prime, and then v hat bar, plus sine squared phi, and then what? And then a v hat, v prime, v hat, like that. Okay. And just where did my sine squared phi go? My sine squared phi, there's a bar over here too, right? Bar. That has to be a bar. Beautiful. Okay. And then plus what? This just gives me phi prime. Phi prime. Now what is this over here? This is sine squared plus cosine squared, so this is exactly just the inner product. These are dot products, of course. So this is going to be what? Dot product, just put our dot products everywhere. And so now what do I have? I really have v hat prime dot what? Dot v hat bar plus phi prime. But what is v prime dot v hat bar? That's exactly the algebraic value of the covariant derivative of v, right? So this implies that the algebraic value of the covariant derivative of w is equal to the algebraic value of the covariant derivative of v plus d phi dt. And this phi is sometimes called the turning angle between these two curves over here, right? So what I've done now is this is going to be this is a very beautiful result over here. It relates the algebraic value of the covariant derivatives with the angle between those two curves, right? So this is the change in the angle between the curves. Between v hat and w hat. And we're going to see in further videos how I can take this and prove Liouville's theorem, which relates the algebraic value of the covariant derivative to the first fundamental form, and that's going to relate things to curvature again. So we're going to use this, we're really going to leverage this idea of the algebraic value of the covariant derivative in terms of angle between the two curves to really get information about the curvature of the underlying surface. Thank you very much.